Bit of background. We're both chemists, so it's maybe I don't know how many chemists you end up with at this conference normally, or certainly chemists that come and talk about color. Um, so we don't have to spend too much time on this. If you want to know the whole long, convoluted backstory about how we ended up here, I'd be happy to chat about it. But the super short version was I had a grad student who kept asking me questions about why we did things the way we did with the design of data visualizations. I had no good answers, and so I figured I should find out. That led to the creation of a course that I teach at Penn State that's on thinking about how to take the tools of graphic design and then combine it with data visualization to help communicate clearly quantitative data. Morgan has been teaching this course with me, and so that's how she's involved here. And recently we also have a grant from the National Science Foundation, and the goal of this grant is to research effective ways to teach the design of data visualizations and then to create materials and disseminate those materials so other people can also teach. And that's sort of why we're here. Okay, so part of the mission of this grant is to disseminate ideas about the design of data visualization and develop materials. So this is the first one we've done, and that hints this survey, so it's going to help us hopefully to understand what worked well and what didn't, where people are starting from, and so we can tune the sort of level at which this is taught. So anyway, that's the survey. I guess that's it. I don't know if you want to say anything or not. Okay, good. Okay, so we'll get started. I think especially I'm just going to give you a lot of my perspectives on this journey to understanding color. And one of the things that I had to come to grips with, especially as I think a technical person, is that color is all about perception. I mean, there are rules, there's math for working with color, all of that's fine. But at the end of the day, it's about how people perceive the colors that they see. And so probably many of you have seen this optical illusion. Just the fact that we have optical illusions should tell you that color is all about perception. If you haven't, the basic idea is that the color of this square labeled A and the color of the square labeled B are the same. Those are the same gray. And so your brain will tell you they are not, even though they are, because it's how your brain is interpreting what it sees. That's really what color is for us. And so that's kind of the world that we have to live in, and the world we have to inhabit is that people's brains are telling them things about what their eyeballs see. Okay, another thing I had to learn being a scientist, I came into thinking about color, and probably one of the reasons I was very confused about color is that I used to think color and wavelength were the same thing, and they're like decidedly not the same thing, right? So I don't know how many of you have taken a science class, but like this is so common, right? It's like, here's all the different electromagnetic radiation, and there's this like narrow wave that we all see, and then like here's the rainbow, and so there's all the colors. And like I never once questioned this story I was telling myself. And then one day I was reading something about this, and somebody pointed out that like that exists. So here's magenta, and it's nowhere in this spectrum. Okay, so color cannot be wavelength for that reason. Even if you look at like all the different like lightnesses and darknesses, there's no magenta in the rainbow. And so color cannot be wavelength. And what it is, again, is like you have this like sensor for photons. And in your eye, you have cones. Probably many of you also know this. And you also have rods. And what you have then are cones that can sense basically short wavelength, long wavelength, medium wavelength. This is a series of wavelengths and then the sort of response curves for those. What's happening when you see the color magenta is that you're seeing like red and blue photons at the exact same time, and that gets passed on to your brain, and then your brain has a model by which it interprets both red and blue simultaneously as magenta. So again, there's no like wavelength that's associated with magenta. It's your brain interpreting seeing multiple photons at the exact same time, and then it assigns it this color, magenta, inside of your mind. Okay, so that means we also have to come up with color models that deal with that, okay? That your brain is able to interpret multiple points of input at the same time. Okay, again, I'm a technical person, so we're going to come at it from a technical standpoint. I think the outline of this talk now that we've gotten started, is that we're going to talk about some of the models for working with color and why some models are useful for picking color and some models are not useful for picking color. Then we're going to talk about some heuristics for choosing color in order to convey meaning. Then we're going to talk about some of the tools that exist for picking color for that meaning. We'll talk about a little bit of other considerations with dealing with quantitative values, and then we'll have some time to play around with some of these tools and ideas. And yeah, anyway, again, also along the way, ask any questions you have. So if there's these three cones that sense color, it suggests that color space is three-dimensional. And you could break down the color space as basically a response. I didn't realize this room would be quite so light, but this is the long cone axis, the medium cone axis, and the short cone axis. And if you were to just scan across all the wavelengths, you would outline a color space that looks like this. Usually people don't like, I mean, it's very hard to look at three-dimensional things, so usually what happens is that you see a 2D projection, maybe looking down the short cone, and also a transformation that we don't have to worry about right now. It's just a linear algebra transformation of this color space, and you'll see this. So this is like a standard representation of color. All right, so this will become semi-important later. The outside line of this are the wavelengths, all right? So that's the rainbow. And then everything inside of it are all the other colors that we can see. And then, of course, here is magenta, right between red and blue. So that's the color space for visual, like human visual perception. When we think about displays, oftentimes how a display works, especially like the most standard ones that we're used to in like phones and monitors and things like this, is that there are pixels that have red, green, and blue light. Okay, and then we mix different amounts of red, green, and blue light. What that looks like on this color space is that we pick values in that color space that correspond to blue, red, and green. That's what you're seeing here. And then we can mix those colors together. What that means then is we're sampling sort of a triangle inside of this space. So there's no way that I could mix these red, green, and blue values to get a color over here, all right? So another thing that you have to sort of come to grips with or accept is that on a display like this, you're only sampling this like narrow subset of possible colors, all right? So when you look at your phone, when you look at your computer screen, there's this whole swath of greens and blues that you really can't represent. And so if you've ever like been out taking a picture of the world and you thought, oh wow, this is like a beautiful forest, and you take a picture of it and then you look at your phone and it's like I didn't capture it, it's probably because there's like this monstrous set of greens that it cannot display back to you after you've taken this photograph. It's also why on this plot, like all these greens look the same, because there's no way for this particular display to represent these greens. All right, so that's just sort of an interesting curiosity, but has practical implications as we move forward. Okay, RGB is a color model, and it's this color space here, and it's how displays make color. All right, so when you're trying to represent something, you have these pixels. And I think because of that, and again, like technical people like ourselves are sort of susceptible to this, that we like to try to work in this model because it feels like this is how we're making the color, so this is how we should be dealing with it. You can represent this triangle also as a cube. And so what you do then is you go back to the idea of having three different axes, a red, a green, and a blue set of axes. And then you just control the value along those different axes, right? So for instance, if I did something like turn the red value all the way up and then turn the blue value all the way down and turn the green value all the way down, I'd be here, and that's maximum red, okay? In this cube, as I like turn blue up, I would move from red to magenta, and then if I turn green up, I'd go to the white point, right? And so it's this 3D cube. You can kind of see it moving around if you don't believe me. This is where no lights are on, and it's black. Okay, so that's like a color, that is a color model. It can be a useful color model when you're trying to actually control the diodes inside of a display in order to get these colors. But it's kind of a useless model, in my opinion, for choosing colors, all right? And the reason is it's like hard to understand, as we'll see. It's a difficult model in which to understand the relationships between colors. So you can find color pickers on a computer that will give you access to the RGB space, but it's this like kind of weird three-dimensional cube, and it's hard to like identify where things are and exactly how some point abstracted in this 3D space relates to another point in that 3D space. So instead, designers have created other models, color models, that help with dealing with color. And probably the most common to find, maybe there are more useful ones, but the ones that you're most likely to find when you're trying to pick colors on a computer are HSB, and it's also called HSV. So there's sort of two names for this, unfortunately. H stands for hue, S stands for saturation, and V stands for value, B stands for brightness. What you do then is you basically take this idea of combining red, green, and blue like we had in this triangle before, and you turn this into a plane that is this circle, so essentially the color wheel. And then you can think of this as being turned into a cylinder from there. So you have 360 degrees around the edge of the cylinder, and that's hue. That's sort of like colloquially what we might call color, or what a lot of people would call color. And as I move around this, I change that color. I like to think about this as almost as if you have like a light bulb. And so it doesn't matter what color my light bulb is. If I turn it off, it's black. And so that's what value captures, is I have a particular point in this cylinder, and as I, again, like basically turn it off or turn it on, and it'll change that brightness or that value. And then you can think of saturation as essentially right in the middle of this cylinder is a set of colors that run from white through the grays to black. And I can mix a pure hue with that white, gray, or black. And that controls then how saturated that color is. Okay, so this HSV is a color model that gives us access to aspects of color that are just so much more useful in design than RGB. And so let's try to illustrate that for a second. We're chemists, so I'm going to show you some chemists. Sorry, this is Lavoisier and his wife, if you did not know this. He was one of the most famous chemists. He was alive during the French Revolution. And beyond like being a person who did a lot of interesting chemistry, he was a tax collector, so he had his head cut off. It kind of like really, this is before that. So it kind of set back chemistry quite a ways. Anyway, you could take this picture. This picture looks like pretty vibrant, right? There's all these greens and reds and blues that make it feel like that's where the information is contained in this, but it really isn't where information from color comes from. And when I'm talking about information in this context, I mean contrast. Like how can I tell different parts of an image from one another? And so you can see that if I take this image and I just isolate the hue channel, this is what I get out of it, okay? It's sort of like, yeah, I guess if you know where it came from, you kind of know what you're looking at. But in the absence of that, it's not so great. I can do the same thing with saturation, and it's not so great either. But when I turn to value, I get something that starts to look a lot like a black and white photograph, right? And so our experience with seeing black and white photographs or black and white films is an indication, actually, that we're very good at interpreting differences in lightness or brightness, but not so much really hue. And you can also think from like an evolutionary standpoint, like if you go out at night and wander around, like you really can't see colors. Those are the rods in your eyes that are taking over. They don't really sense color, but you can still navigate just fine. So the color channel's, you know, sort of an ancillary bit of information. You can also think about just removing a single aspect, so do the same thing, but like let's strip out the hue so that all we have is saturation and value. That really is pretty much what a black and white photograph is. So now we have almost all the information that we can have, whereas if we remove the saturation or the value, like when we get to removing the value, you know, there's a little bit of information in the hue and the saturation, but it's not nearly as nice as what we're used to seeing here. This idea of combined saturation and value is sometimes called luminance. There's a whole nother color model for this, but we spent enough time talking about color theory. So if you really want to know about it, we can talk about this like a CIE lab space that's trying to capture this idea of how humans like see and perceive color. Okay, but the point is this luminance or this brightness is really like one of the best channels we have for conveying information. All right, are there any questions so far? You don't have to have them, but I'm happy to, or arguments. You can also disagree with me, it's fine, yeah.
Not a well-known question, but in my mind right now, I'm thinking there's got to be like there's linear algebra going on.
Yes, absolutely.
I can't map it into my normal understanding of like vector spaces or tensors or something.
Yeah.
Like that. So without going into too many gratuitous details,
Yeah.
What's going on with the math behind this?
Yeah, so the math, okay, so it depends. So we started with this plot that's like your cone responses, okay? So when people are trying to map onto, so different color models have different like purposes, okay? So when we're talking about this and we're trying to reflect like how humans perceive what's going on, they take the long, medium, short cone responses, and then yeah, you undergo a linear algebra transformation that attempts to make it so that colors that are if I took two pairs of colors and they were equal distances in the space, then people who are asked about how far apart these colors are would perceive them the same. And so it's very empirical because again, color is based off of perception. And there's a lot of crazy aspects that go into perception, right? So the brightness of this room changes how we perceive the color. Actually, the angle through which you view color changes the color. So if you take like if you view like a solid piece of color and you view it through a hole that's like this big versus a hole that's like this big, you will perceive that color differently. And that's because like the distribution of cones and rods in your eye is different. Like the cones tend to be right near the focal point. So that when we have bright environments and we're able to like focus on things well, that's when we're trying to perceive color anyway, yeah. So there's like these spaces that exist for different solid angles of viewing actually. Okay, on the RGB space though, that was never its intention, was to mirror human vision. Instead it was to control diodes. But then, you know, like we all code and then we get to these like HTML or like hex values and they're all basically just RGB values and then everybody starts thinking about things in RGB space and it's like problematic, yeah. Yeah, does this answer your question?
Yes, yeah.
Okay, there's a lot of great books on this. So if you really want to dive in, I can give you some recommendations on that. Yeah. Okay, other questions? Yeah.
So when you explain about how different angles and lights can affect how you see a color, like do you define a color as in that one of those scales and that's it, or would you put other factors into part of a definition of what color is?
Yeah, so it depends on so the question is, how do I think about what a color is if it depends on things like angles and when I'm designing? Okay, so one, you kind of have to come to terms with the fact you cannot control the environment under which everybody will view your designs. So you kind of have to build it in, right? If you build a design that has very subtle differences in color, it could easily fail. All right, so you have to keep in mind that when you're trying to design. The other thing that happens is, yeah, the solid angle matters, and so like if I had, I don't have a slide on this, but if I had two fairly bold lines that were easy to tell apart in color, and then I make them extremely thin, a lot of people won't be able to tell them apart anymore. So like size also matters, and our ability to like look and understand. So one of the like golden rules in design is like, yeah, you might have picked good colors that you think work well when you're looking at these big swatches, but like you should always look at the final design and ask yourself like, for real, can I tell these apart? Or ask a friend, yeah. It gets even worse. I mean, I don't even worry about print. Print's a whole nother problem, right? Like whether it's matte or glossy, the light that is viewed under all of this controls color, yeah. But we'll just pretend, because most people probably do just look at things on their displays, that we're gonna think about displays here. Yeah. Yeah?
Do the TVs that have the yellow pixels, do those actually add any value, or is that just a sales goal?
It can increase, like what the technical word would be gamut. So depending on where this is, it can increase the gamut. And there's like mathematical tricks you can pull where you pick like imaginary colors and use those, like colors that are outside the gamut we can actually see. There's colors that you can see that you normally can't see. We had this like cone response. So there's a trick whereby what you do is you like look at a bunch of red, a whole bunch, and that saturates the red cones, and they no longer report color. And then you look at a blue color, and now you're seeing that blue color without stimulating the red cones at all, and that blue will look different. I mean, there's like all these like crazy tricks you can play with. Yeah. Okay, I'm trying. Hopefully, this isn't yet seeming like an impossible task, because it's not. But it's just one of these things that color's very rich. Okay, more questions. Yeah.
So I know there's some displays that they market as color true. Are they just more color true, or are they truly able to capture the spectrum?
Yeah, I mean, it depends on what you're trying to say by color true, right? Like, if you're...
That's a really fancy one, right?
I mean, so there's like a lot of... There's two ways that you might think of making... Let's just step back a second and say, like, what a high-quality display is instead of, like, color true, which may be a bit market-y. But there's two things. One is, like, how close together can I put things in color space and still represent them in a way that people will see them as different as if I had painted them or something, that I had this, like, analog control over color. The other is, if I were to tell somebody, oh, I used these RGB values, and then we could agree on what that was, and then they went and looked on another display what that was, how similar is that? So it's like the reproducibility across the display. And then there's finally, like, does that actually match what the model says it should be? Right, because you can have, like, drift in the display. I mean, especially when you have, like, old school displays where you basically have, like, liquid crystals that you're projecting light through, and, like, what is the actual temperature of this light coming through? Yeah.
I was actually getting at a slightly
Okay.
different question, but that was all really interesting. But the triangle you showed where all those
Yeah.
things we can't see, are there any displays where you can see that hole?
What you would need if you wanted to see that entire human gamut is something that could produce light at every single wavelength. So what happens, I'm not aware of anything that has done that. So let me answer that question. But there are color spaces where people have like 5 or 6 maybe different color sources, and that widens the gamut. Yeah.
Oh, right on.
Yeah.
Thanks.
But I think like most people, until you tell them like, yeah, you're not crazy, like you took a picture of something where you can't see it on your phone, like never think about it. So functionally, we're all kind of okay just accepting that we don't see stuff.
Sure.
Yeah. Other questions? Okay. So I guess this is the end of the theory portion, and we're going to talk a little bit about like what do we do with this knowledge. Now that we've like created an impossible task where there's like 7 million colors and nobody can actually see the same thing twice.
All right. So just to remind you, my name is Morgan. I am a PhD candidate at Penn State. I'll be defending next month. I started thinking about data visualizations when I took Dr. Lear's course last year, and I'll be doing a postdoc with him working on that NSF grant. So this is why I'm here, and I'm interested to talk to you all. So we're going to talk a little bit more about like practical applications and how do I think about actually using the color space to make good visualizations. So the simplest heuristics are based around the color wheel. So this is kind of where we ended with Dr. Lear, thinking about the color wheel, and we are going to focus on how we use these hues to actually create meaning and tell stories. So there are sets of colors, pairs, and triads that you might have maybe seen before, but might not have really thought too much about. Has anyone heard of these types of things before? Yeah, okay, good. So I'm just going to show you some example data visualizations that intentionally use these different pairs and triads in order to tell a story. So first we have monochromatic, and this is something Dr. Lear will talk a lot more about later. But you might see an ad like Hall's Cough Drops, where it's really just using blue as the hue, and we're thinking about just changes in the lightness and saturation. And in a data visualization, this is best used for color mapping because we're able to really easily compare the darkness to know like population density or any other densities that you might be thinking about. So Dr. Lear will go more into depth about this in a little bit. One of my favorites that I like to use are the analogous. So this allows us to look at colors that are very close together on the color wheel. And these can be used to show that things might be like correlated or similar without necessarily giving, just showing they're all related and maybe going in the same direction. So one example, we could think about the concentration of carbon dioxide rising over the last 3 decades. We can show each of the decades all similarly rising. They're all kind of trended up in the same direction, but I can differentiate them by using 3 different colors, but show that they're related by those colors being similar in location on the color wheel. You could also use something like complementary, where these are opposite of the color wheel. This is one of the other ones we use quite a lot, especially in storytelling, because it's really important for showing contrast and helping the audience pick something out about your data. And sometimes it still makes fun logos. But for example, this is from our general chemistry honors course. This could be quizzes and homework scores, and using not just the color, but also the shape of the marker. They're both contrasting, so this helps tell the story that the distribution is similar, but we can pick them apart very easily when we look at them. No, question?
Orange and blue also means it was the Excel default and I left it alone.
I mean, yeah, if you've been alive, I guess since like 2000 or something, right? It used to be green and red before somebody pointed out that was a bad idea.
Okay. And then you can also start to do things like split complementary, where you might have 2 things that are related and 1 thing that's very different that you might want to show. So for example, we could think about, since 2000, our housing and education costs are going up while our income is nearly the same. So this is also an expense that we might have. This is money coming in. So there's different reasons we might want to show the contrast between them. But the red is very contrasting to both the green and the blue, which are both showing a rise together. And then if you have 3 things that are each contrasting, you can use something like a triadic color scheme. Many of you might be familiar with Aladdin uses this. But say spending, like we have science, health, and the military all going up and down at different rates, different times. And so each of them are different, and we're kind of showing that through the color. So all of these color schemes that we've used are trying to help the reader without necessarily them knowing that you're telling the story in that way. And there's so many others that actually exist. So squares and rectangles and all kinds of things, if you start Googling, you can go really deep down a rabbit hole of different schemes on the color wheel. So what we're going to do is think about a few things, and then we're going to look at some tools. A few good pointers. You can have too low or too high of contrast. And some of these things make the visualizations hard to read. I mean, even on this screen, it looks different than on mine. This is like lime green on my computer screen. So like Dr. Lear was saying, it matters what you're projecting. But if it's too low, people will have a very hard time differentiating. And then like we were saying, the width of the line could also influence, like these bars are very close together and they're touching, and so the contrast makes it hard to tell them apart. You also need to think about accessibility when, sorry.
About the last slide,
Yeah.
do you recommend any tool, because there are tools to check if there's enough contrast for accessibility standards and
Sure.
so on. Are there any tools to check, like do you recommend anything to avoid too high of a contrast?
Yeah, we'll look at some tools in just a minute, and I'll show you how you can like play with them and test it.
I'll just mention real quick. I think there's like microphones up here. I'll catch this, right? Or okay, all right, maybe not. I'll just mention. So the question was about tools for like low contrast versus high contrast, and yeah, there are tools that check contrast, and it'll tell you if it's like too low. Although, I mean, like that research is a big mess too. But like too high, there's one of 2 ways. One, for a lot of people, this will feel uncomfortable to see something that looks so high. But the reason is that you have like a very bright color, so something with a high brightness or a high value, against something with a very low color, and that's when you start to see this. This is where good contrast comes from, but like if you are starting to pair something that would be like a fluorescent color with something that would be like a jewel tone, you should probably like think about that, right? So jewel tones would be like low brightness colors, yeah. And you could, I mean, like your friends and colleagues are good resources for this. Like a lot of times when things are very high contrast, I'm not sure if this is good enough. It probably isn't for this effect. But if you've ever seen something where it looks like where two colors meet, it's almost like wiggling. That's an effect that happens when it's like too high contrast, and it becomes uncomfortable for people to look at.
So the other thing that you want to be careful about, just in general, when you're making visualizations, is accessibility. And so, here we go. Pardon us for using normal vision, but like Dr. Lear was saying earlier, red and green used to be the default for a lot of things, and for some reason people really like to pick it. They are contrasting, but when you look at this through somebody else's eyes, you might not see the same thing. And so it's really important to check for color blindness. It's really common, especially among males, and I'll show you a tool that will also help with this. So we're going to go into the tools now. So there are some websites that are useful for making palettes. We have this colors website going to pull up. And there's a couple ways that you can use it. The first is just by going to the generator. And the generator will give you like a random start. Make this bigger. And so right now I'm looking at a palette that the computer gives me. But I can do things, lots of different things here. I can say, wow, this like blue is something that I really like. I want to build a palette around this blue. And as soon as I push my spacebar, all of the other colors change if I lock it. Maybe I also only wanted 4 colors in my palette. I can delete colors and I can add them. In the free version, I think there is a limit of like the maximum, but it still is very good. And I can just generate different colors. Now, if I'm looking at this and I'm like, oh, I like a second color, I can lock it. I might be interested in a different brightness, so I can click there and choose the brightnesses. Maybe I wanted it to be a little brighter, and I can lock that in. And then I might be thinking, well, blue is one of those colors that can be hard to see if there's a purple around. And so this actually has a very nice feature that has these little glasses at the top up here. And if I click it, there's different options and different types of color blindness that I can check it for. So this, if you are not colorblind, this is what it would look like to us. But if you choose one of the types of colorblind, this is what it would look like for that person. And so this can be really nice for you to get an idea of what are people going to see? Because some things that might look contrasting might start to get a little bit closer when we look at other forms of color blindness. Okay. Any questions about this tool so far? Okay. This tool also does have palettes that are already made. So you can scroll through, there's lots and lots of options. Some of them are just one hue, some of them are, just what people have made. You can click on them, you can use them, you can open them in the generator if there is maybe only one color that you didn't like. And another nice thing is you can get the hex code from them, but you can also change the different model that you're using. So you'll see that I could make it red, green, blue, but I can also do the HSB as well. So depending on where you're going to be importing these colors to, it's a really nice tool for that. And so I can change things manually for the one color and then just continue on generating. So it's a very fun tool. Play around with it. There is another tool that you can use called Viz Palette right here. I'm going to pull that up. And so this one, let me make it bigger, actually does something similar. You can pick some colors over here. You can add or take them away, and you can change actually what color model you're working in. But the nice thing about this one is that it's actually showing you different types of visualization so that you can see, like maybe I don't like how close these are together, the colors are, because the lines become harder. But if it's something like a violin plot that are separated out, maybe I don't care as much. So it's nice when you can actually see what type of visualization you might be creating. And this one as well has some options for you to see the color blindness as well. And you can see like some of the colors blend for some more than others. And it's always nice to check the grayscale. And then we have one more tool to show you and play with. And this is a color blindness simulator. And so one of the things that you can do will not only simulate, but there are tools that you can plug in the visualization that you've made in order to check the final product. So if you're like, okay, I think these colors are good, and I've generated my visualization, you can upload it to things and actually use it to check, did I do a good job? And so what we're going to do is just spend a little time trying to build a color palette. Or if you already have one you like, or you pick one quickly, try to use it on one of your visualizations. And we're going to just walk around for a little bit and help you workshop, answer questions, and we'll spend like 20 or so minutes doing this.
I don't know what you want to talk about mapping.
Oh yeah. Oh, mapping first, then we'll play. Mapping first.
Work first.
Work first.
Yeah. All right. Yeah. So I think, and if there are questions, just again, anytime you can just yell at us. This part of the talk is really thinking about, or was thinking about, what I would call like categorical color choices. So not necessarily trying to map back a quantitative value onto color, but how do we like help somebody process the relationships that we've seen between data or within data inside of our data. All right, but there's also the idea that we sometimes want to map quantitative values onto color, and that comes with it its own sort of considerations that will ultimately, again, come back to this idea of thinking about lightness in color. All right, so color maps, you already saw one example. So this is an example of voting results in the United States during maybe a presidential election 2 elections ago, maybe. This is a map of global temperature as a function of time. And so we have a calendar represented by the circle, and then you go around year by year by year since 1880. But the line that is generated is quantitatively mapped onto color based off of the temperature that was observed, okay? But you can make bad choices, okay? Those two were pretty good choices. We might have some quibbles about them. I would call these generally bad. It makes it difficult to understand quantitatively what's going on with the different colors, okay? And the reason for this comes back to a question of lightness. I think a lot of times people pick these sorts of like rainbow palettes because it feels like before you understand how color's behaving and you realize that hue isn't really where the contrast is, it feels like I'm going through all these different colors, and so shouldn't that give the viewer like the most granularity in understanding what color I have? But it comes back to a question of lightness or luminance, okay? So this is like a rainbow plot. This comes out of Matplotlib. We'll talk about, if you don't like, I don't actually use Matplotlib, but their color documentation is spectacular. So this is one of their plots. This is a rainbow plot. You should not use it, but it was used to map this data here. And sort of the problem is, if you look at the grayscale image for this, it kind of fluctuates. So it starts dark and gets light and goes a little darker again and light again and then dark again. And so you don't have this sort of uniform, perceptually uniform in terms of the lightness across this color scale, right? So again, thinking about that our contrast comes from these variances in luminance and this like CIE lab space, we're not gonna worry about too much. When people pick this rainbow, it feels like this is what you're doing, right? Again, in the RGB space, we're just like exploring a large swath of this RGB cube, And so it feels like you've spread out your colors. But in this CIE space, what you've really done is you've like wondered, if this is lightness up and down, you've like wondered around in terms of lightness and led to this confusion. Okay, so if you tried to take this black and white image and just color it using this like rainbow, it's much more confusing to understand what you're looking at here. And all I've done was I took, dark to light colors and mapped them across this exactly how you would do if you were trying to map quantitative values onto this color scheme. Okay, the monochromatic works great. I mean, it just looks like you're trying to be a little artsy, and you've taken this like black and white photograph and made it a little bit blue, because I guess they're sad that their heads are going to get cut off. Okay, you have this like fluctuating scale. It does, it's not, the point I want to make here is it's not that I have a bunch of different hues and that leads to confusion. It really is the fluctuating lightness, because I could pick a color scale like this that has several different hues throughout it, but is still going from a dark color uniformly to a light color, and this will look much easier to interpret than this one here. So it's not the multiple hues that is the underlying issue. It's the ability to go from like a dark color uniformly to a light color. And so this is like the scales mapped against the lightness. And so yeah, you can see this one kind of comes up and then back down. These are both like fairly linear responses in lightness. Okay. Another nice thing, Morgan talked a little bit about color blindness. So these are the common forms of color blindness, the most common forms, and then grayscale, which is again reflecting this variation in luminance. But if you take something like the scale we just saw and then look at it under different forms of color blindness, it's actually still fairly easy to interpret what's happening, because again, the channel that's carrying the information is going from dark to light, and that happens no matter what color vision you happen to have. Whereas you lose so much information here because a lot of the information channel was trying to be carried by the hue, which is inefficient at doing that. Okay. Also, something to think about is like this is just one kind of color mapping. And so we've been talking about what people would call continuous sequential. So you have a range of data that runs from like a low value to a high value, and how would I carry that or map that onto something like this? We saw that in this map. Maps like this are very common. You could turn it from continuous to discrete, so maybe you have binned data, maybe you have categorical data where you have like counts, and so they can only come in very particular values, and so you can turn a sequential continuous plot or color map into a discrete color map fairly easily by just binning that color map. That's okay. And you'll see this a lot of times when you see these sorts of like choropleth plots, okay? You can have data though, where there's like it doesn't even have to be central. In this case it's central, but where there's like a unique value that we vary against. Okay, so a very common map that we see are like election maps, where there's like a 50-50 split in the vote, which means neither party is favored. And so that 50-50 has a special value. And so then what you tend to find are maps that would have a central point that's light or dark, depending on which way you go. And then you basically have uniformly varying to dark, in this case, on both sides. And then you use hues to create categorical values. So you're now leveraging the hue channel to tell somebody, I think those of us who spend a lot of time looking at politics in the US would just immediately be like, the blue is Democrats, the red's Republican. That's like the categorical statement that's being made, but then the intensity of that maps onto the lightness and the darkness. Okay, you can also have something where like the value resets as you go through it, and think about maybe like a pie chart is a great way to do this, where you might have something about, well, in this case, you can sort of see that we have some information about the Americas separate from the information from the rest of the world. And so you create two categories that are still somewhat related. So we have a kind of an analogous color scheme between purple and blue, because we're talking about something about land masses or continents. And then we create two categories within them by having two different hues. And then within those categories, we can have something that varies from light to dark and resets as we change the category. So that's another way that one can use these in order to then, quickly at a glance, right, without having to write anything, without having to take time to explain what's going on, many people will look at something like this and understand that there's like probably two different things happening on this plot. Okay, and then you have cyclic, so something like the seasons or something like this, or like you have something that has radial dependence. This is a bad use, I think, maybe of this particular color scale, but you do see it used in things like fingerprints, where you would be mapping the direction of like the swirls in the fingerprint lines as a function of angle, and so that's something that's clearly cyclic, and you can map it onto something like this. So you have many options for trying to map a quantitative value onto something that is based on color, but in all cases, it will be most effective if you think about the lightness, and so that's what these wedges are showing, is essentially, well, how does the lightness vary as a function of the value? All right, are there any questions on this? There are some tools. You can use the same tool you saw before. A very famous one is called Color Brewer 2.0. And I won't demonstrate it, but if you want to go in there, they have a whole series of different kinds of color scales that have been vetted to be effective. And so you can pick whether you have sequential or diverging data, whether you want to not have it be quantitative but qualitative instead, how many colors you want to have, whether you want it to be colorblind friendly. Developed by a woman named Cynthia Brewer. She's also a professor at Penn State. And generally for representing like geographical data, but it's quite useful for people who are using any sort of data that you want to try to map onto a quantitative value. Okay, if you want more information, like I said, I don't use Matplotlib to plot data, but this particular documentation is beautiful, all right? Like it really walks you through why do these different maps appear, when should we use, what should we avoid. It has links to many primary sources in the literature, and then also other books that you might want to read about this. So this is the place I would start if you want to think about color mapping, is the Matplotlib documentation. Whoever wrote this did a brilliant job. Yeah, okay. And so, oh yeah, then we have this like, I guess now we have time to play. So I don't know, like I said, this is the first time we did this. We thought we might just give time for people to like look at the tools we talked about or ask us questions or try to use it in data visualization so we can just wander around and have conversations with people about that. And this ends at 3, okay? So we'll come back at like 15 minutes till or something like that and wrap up. So that's where we're at. Oh, was there a question? Yeah?
Well, no question, but it just made me think about the fact that, like, when you were talking about the way you sort of orient the color, is it sort of basically to sort of like summarize what's the point of the story?
Yeah.
This point of the story is it's divergent data, then you should have divergent color.
Yeah.
And the sort of just the direct mapping of like what's the point to the color scheme.
Yeah.
And like it looks cool and fun.
That's right. Yeah. I mean, so I'm always asking myself a few things. One is, what have I seen in this data, right? Like, what am I trying to convince another person about or communicate to another person? And so this is another channel for that information, right? And so exactly, like, you could take the same data and apply a sequential color scale or a diverging one, and somebody will reach wildly different conclusions about that. So if you think there really is a central value, picking a diverging color scale is a subtle but powerful way to get people to also see that you think there's these diverging values. Yeah. So it's all about communicating meaning, as you say. There's also, we didn't talk about this, but we have like words like warm colors and cool colors, and so it's not an accident that on this plot of the temperature over time that the warmer colors were red and the cooler colors were blue. I mean, there's like these sorts of cultural associations that you could try to tap into if you know the audience you're talking to, but it is about meaning. And sometimes, I mean, there's like a book, it's called like The Medium is a Message, that's in the art world, and sometimes the message is like, oh, this is fun and playful, and you pick color palettes for that, but that's sort of an expert approach to things, yeah. So, but yeah, I appreciate the comment. I don't know if you have more to say.
No,
Okay, yeah. Yeah.
Is there anything you've seen in the, you know, you mentioned Matplotlib with the documentation side, but have you seen anything that really like helps you out with, if you're doing charting and stuff like that? You know, I'll have to go back now and, now that I know what I'm looking for,
sure.
and see if there's stuff like in Plotly or.
Yeah, so so Plotly is the one I use a lot, and I would say the color maps are not as nice as Matplotlib. They have some good ones, but those color maps, because Plotly comes out of like an older-ish library that hasn't been updated in the color side of things the way Matplotlib was, they have a lot of older gradients that aren't like totally perceptually uniform. So this is like a quasi goal of mine, is to help fix Plotly colors, but we'll see if I get around to it. But if you're, you know, for people who can code like all of us, what I'll often do is I'll just like, this information is published. Like, what are the colors for this? And then Plotly does provide access, like in the API, for building your own color gradient. So I'll just build the one I want. And it's not that hard to do. Yeah, we could talk about that some if you're interested. But it would be nice to be able to like, I envision a tool where people just give it like 2 hex values and it gives you a perceptually uniform color scale between the two. That would not be very hard to build. Yeah. Here and then in the back, yeah.
I'm just curious, like how good is or can it be like using AI for some of the like being able to create like nice visualizations and color maps? Like I feel like when it comes to coding, because I've been doing this for a very long time, I'm just like, I don't trust or I don't like what it gives me from like code. It doesn't look like I want. But honestly, when it comes to the plots, I'm like, I don't really know much, and I wanted to do a nice job for me.
Yeah.
And I just accepted.
I think, well, okay, so for using AI tools, it depends, as always, on how it was trained, right, and the prompts you give it. And so if it's just like some general whatever, and you're like, make me a nice plot, it could give you something that's like a rainbow plot, right? Because it's like there's so many examples of people making plots with rainbow plots because they like are colorful, and you'll get in trouble. But then I would say, like, as you like develop the language, so for me personally, like a huge part of understanding color was really just understanding the vocabulary. Because now you can go into an AI agent and be like, I need a diverging uniform color scale, right? And I would like it to reflect this sort of color palette that I'm dealing with, and then it can do a very good job. So I think it's like the same problem you would have, or that maybe all of us would have when we think about using it for just general coding tasks, right? If you just give it to a student who knows nothing about coding and they're like, build me an app that does this, like it's probably gonna be a hot mess, right? And it's just like not worth dealing with. But as soon as they understand like, oh, I need an app that like has this kind of interface and it has this back end, then you can start to like refine what it gives back to you. And the same thing will happen here, yeah.
Yeah, I might also add just, so when I took Dr. Lear's course last year, he did teach the course out of like ChatGPT rather than, you know, full coding at that point. And at that point, I didn't know any coding. And so like he was saying, it's not just the color that you need to know about. For a good visualization, you want to know things about what you want aligned and where things are close together or far away, and like making the title a claim. And so like what I did as we went along was built a custom GPT that had all of these very specific design principles. And then I would use it to chat back and forth, like drop some data. It'd give me something that's maybe not exactly perfect. I would continue like chatting back and forth until I got something that I was okay with fixing in, say, Adobe Illustrator. And then one of the other things, because at that point I didn't know coding, but I was like, this is a really nice looking visualization, is I would then ask for the code and then save that onto my computer, and then I could just change the files. And then, you know, if I needed to go back into Adobe later, I could. And so I found it very useful for, you know, the descriptions. And I think that's one of the things that we're trying to get at with teaching in this way, is it's all about like knowing the design rather than just what's the basic output that you get from Excel or something else.
Yeah, and as the point was made earlier, like there are tools of design, but the basic function of design is to communicate meaning, right? And to tell people how to interact with objects. And so you really have to know too, like, what is it that I see in this data that I'm trying to express. And then hopefully this helps like develop that vocabulary. So you can go from, oh, I see that there's like a value that repeats over and over again, to, oh, I need a cyclic, perceptually uniform color gradient. You know what I mean? That's the goal, is to help connect what I think many of us intuitively understand we're trying to communicate with like what's actually out there to help us do it.
Yeah, and it saves a lot of time. I mean, for students, say like looking for the button in Excel to do the exact thing that you're looking for, like sometimes it's hard to find, it's hard to navigate if that's not something that you do every day, especially as when we teach this course, it's for anybody on campus, so we can have a music major or history major. And so if they're just describing what they want rather than looking for the button, it's helped us like through teaching the design.
I don't know if we answered your question.
No, that was great.
Okay, yeah, and yeah.
I mean, what terrifies me when you say AI on color selection, it's like, I think in college I had some talk about like what to wear to an interview, what to wear in an office, like,
Yeah.
what you see people wearing on TV.
Yeah.
Not is to grab your attention.
Yes.
Not to accurately portray what actually will happen.
Yeah.
So much of the imagery on the internet right now is to grab your attention,
Yep.
which
Yep.
may not be what you actually want, right? The lime green next
Yeah.
to right.
Yeah.
So just be aware of that. We've all seen, certainly cases where somebody means well with the rainbow and it just winds up being noisy.
Yeah.
Certainly the bad visualizations where their choice of where to put the axis and stuff, they are deliberately obfuscating.
Yep.
Have you seen cases where the choice of color was to deliberately shade, obfuscate, mess
Right.
with?
I mean, are you aware of Hanlon's razor? I don't know if you know this. Okay, yeah. So I just meant, so the reason I bring this up is I tried not to ascribe intent, but yeah. So for people who don't know, Hanlon's razor is like, you should never ascribe to malice what can be ascribed to incompetence. And so like I always think like when I see these like things that could be categorized as misleading, maybe it's just some like random intern who started that day and they're like, make me a bar chart, and then they made a bar chart and then they're like, no, make it look good, and then they clicked all these buttons and it like truncated the axis. And but I mean, so there certainly are people, bad actors out there, but
If someone's trying to say, look at this
Yeah.
huge difference, and of
Yeah.
course it's a difference of 0.001%.
Yeah. Yeah.
Right? And they're telling you it's a huge difference, and now they've chosen a massive spike in the color.
right.
Right? Then that's part of the message they're trying to convey.
That's true. That's true, right? And so I also, this is maybe a question that we could spend a very long time on. Like I actually have very strong opinions about like the like moral, moral is probably the right word. Like the moral obligation we have to help other people see what we see, which really is about biasing how they look at a design, right? You want them, for instance, this design was not just like take all the words and images that I think pertain to color and then just slap them in there in no particular order and then good luck everyone. It was like think about what makes a logical argument and what's like compelling and leads people to see the same things that we see. Anyway, but to answer your question, you'll start noticing this if you look at color scales where like there's a bunch of like dim pastel colors and then one that's like bold and stands out. And okay, it's either somebody trying to draw your eye. Well, it's always somebody trying to draw your eye. And then you have to ask, like, why is this happening, right? So part of it, unfortunately, is being a savvy consumer of media and asking yourself, like, why did somebody put contrast here? And maybe it's because they don't know what they're doing, and maybe it's because they're trying to mislead you, or maybe it's because they thought about it a whole lot and they don't want you to have to spend a lot of time thinking about it too. Yeah. Other questions? Yeah.
So we saw the rainbow
Yeah.
thing, right? And then when we used it on a geographical map, but then that was not recommended because there are a lot of information, a lot of contrasting colors. But then we see the same pattern in a storm map. That's a map, but then there are storm warnings. If it's red, it's more likely that's a storm targeted area. So how do we choose how to place that rainbow palette in maps?
Yeah, so there's maybe two questions when we think about like the weather maps that oftentimes do employ things like rainbows. Sometimes they use good rainbows, right? So there are rainbows that like go from dark colors to light colors, and that is much easier for people to interpret. But also, there's like conventions, right? So you're never designing in a vacuum. you're always designing inside of some culture that's expecting certain things to happen. So Morgan pointed out that like red and green are not colorblind friendly, but like just open up any sort of like financial chart, and green is profit and red is not, okay? And that's a problem. Like many of those charts are very bad at being colorblind friendly. And yet, if you don't make a chart, this red and green, you'll give it to somebody and they'll be like, what, like, why isn't this red and green? And so you have to like understand the conventions that you are within and then decide like, is it worth the like, one, putting up with everyone's complaints when I don't do it, and two, like even the cognitive load of your viewer who has to look now at a chart that's orange and blue and be like, well, which one of these is profits, right? When they're used to just glancing at it and being like, the green stuff is good.
Yeah, and I think like this is something that is changing, you know, little by little. I mean, we were also at another visualization conference recently, and it's like there are always standards, and like I had a paper submitted to like a beer journal where they don't care really about any of the colors that we use, but then we submitted to an education color and they could not handle gray axes. But the point of the gray axes was to not have this black, you know, black axes, which are very contrasting to the white paper or the white screen that you might have it on. And like they just did not accept it. So like little by little things are changing. And I think, you know, if it's something that you think more about, it's something you can make a difference like in your field, you know, as we all start to think more about those changes.
Yeah.
So I have two questions.
Sure.
First one unrelated, but is
Perfect.
your jacket random or just
Oh,
to prove the point?
No, I mean, yeah, I thought about it deeply, and this is definitely not the warmest fleece I have. No, I like orange, you know, a lot as a color, and I don't know, maybe people think it's red. To me, it looks orangish. I don't know. I guess we can have a discussion about that, but I like orange. That's why. Yeah.
Yeah, word contrast.
Yeah.
And second one, I think if say like I walked out this workshop and I'm gonna make a map, a graph, then what is your advice? Like step by step of like what I should consider like, color for the graph.
I mean, for me, Morgan may have a different opinion, but for me, I would start with like, what do I think is the important thing I'm trying to convey here, right? And then, what does that mean in terms of these heuristics that you presented? Like, am I, you know, I'm talking about categorical stuff now, right? Should I be doing something that is leveraging two colors, and then should it be contrasting or not, right? Or should it be analogous? Is it something that I'm trying to show like three different things being related, and now I'm either triadic or analogous or split complementary? That's how I view this. Like, and then once I've made that decision, then I start thinking about like, well, what's the color palette or what's the feel that I would like to have, right? Like, do I want this to feel cool or warm? Do I want the, like, one thing we didn't talk about that I use a lot of times is like, maybe I have one thing I want to stand out, and I will give hue to, and everything else will be gray, right? And then people will like cue in on that color. And so when I'm really trying to direct attention to one particular thing, I'll make that like a deep red or a deep blue against a light gray. And now I'm leveraging lightness, but also the fact that like one thing has color on this like page that's typically like black and white text. And then your brain is so good at teasing apart what's different in the field of vision. You know, like basically we have millions of years of evolution about not getting eaten by things or trying to eat other things. And so like we're very good at finding differences for that reason. And so I think about that, like where do I want attention? We didn't have time to talk about contrast and like those tools of graphic design, like contrast and proximity and alignment, but these all kind of like play together. So, and then the last point is to iterate on that, right? Look at this and be like, is this telling the story I want it to? Once you think it does, show it to somebody else and see if they reach the same conclusion, right? Don't tell them like, I'm trying to do this. Be like, what is this telling you? And then think about like, are they cluing into the same thing that you want them to?
Yeah, and one of the useful things for me is like basically the same order of steps, but when I'm trying to think about the story, I think about like what's my one sentence summary, which ends up usually being like the claim that is the title. So it's like I'm trying to think like what is the one thing that I'm trying to show in, you know, most simple terms, and then that's kind of what I use to tell the story.
Yeah, I think having a clear message is the most important thing, and then everything else is in service of that. Yeah. Does that answer your question, or?
Yeah, yeah, thank you so much.
Okay, yeah.
Just a little bit following up on
Sure.
that and what you had mentioned earlier about like how you had that like assistant that you were kind of talking about. Like so, like when you say like you think about that message, is that something that like you still feel like you need to translate to like this is the like color terminology and the way that I want to express that from the message, or like what with what work you did? I'm just really curious about that. Like, did that kind of go from the like could you essentially go from the message and it would give you stuff based on that?
Yeah. I'll just speak for myself. Like I have not asked usually like an AI agent, like this is the message I'm trying to communicate, give me a color palette. Instead I've thought about like what might be the thing that serves this and help me make that color, I kind of have it in mind, but I've just never tried what you're suggesting, and it might do a fine job. I haven't tried it. Yeah.
Yeah, I haven't asked it specifically like about the color, but I do have it set up to try to make a claim about the data originally. So like I can judge like, is this the same thing that I get from the data? And then of course I can just change the title if I disagree. But yeah, I haven't asked it like, what do you think the best color scheme would be? And honestly, like once I have a palette that I really like, because my research, continues on and I want my papers to kind of string along and connect, I continue to use the same palette, like for the same types of data. So once you do the hard work to make a palette, like keep using it, because you'll save yourself time in the long run.
Yeah, I mean, I don't know if everybody has the same sort of luxury, but like my research group, we sat down and made a style sheet, like this is what designers do. So we had like, what are our colors? We made sure we had a color palette that was colorblind friendly, that had colors that could build triadic, could build split complementary, could build analogous colors into it. I mean, this took us weeks. Okay, it wasn't like an easy thing, but it's, good things are seldom like something that just happens like that. But we also did like fonts. What font sizes? What fonts are we going to use in what parts of this plot? And like, what sort of like alignments do we want to have throughout? And like, what kind of like tick mark styling do we? It was like sort of painful. But now we have this thing that we make plots that look like our plots.
I just want to quickly point out is that like if you use Matplotlib, you can create a color, like a patch of code that is sort of like your group's like style guide.
Yeah.
Because I did that for a group, right?
Yep.
Wrote it, and there's a lot you can control in there, and then all of your charts and graphs come out in the colors you want to use.
That's right. Yeah, and you can do it in Plotly as well. I mean, that's the one I'm familiar with. So we have, in fact, a series of templates for Plotly that vary on where we're publishing, right? So it's like this particular journal, it'll format it for that journal. With like, so.
Sorry, do you have recommendations for like, in terms of like, okay, I'm working within a corporate color scheme, right? And I recently tried to do this where I created a custom Matplotlib, like color map, linear segment with like a couple of the corporate colors. And I'm like, it looks okay, but not great. But I think it's a sort of like sequential luminescence that's the problem. Do you have suggestions for like how to prompt better? I don't know, like what terms should I be trying to like incorporate into trying to figure this out? And like
for prompting, I don't know. In the tool, I don't know if we can go back to this tool.
My plan is to like plug it into some tools now and try to make a couple of different things. But like the corporate constraint is a little
Yes, well,
because you can put you can change the colors that you want to start with and lock them, and then like play with it.
But at the same time, it could be that like they just don't ever make a you can't use all the colors, right? And how to
Yeah, that's right. I mean, you'll see companies do this. Well, they'll pick whatever their dominant color is, and you might build a monochromatic one around that.
Yeah.
I mean, the
dominant color is like bright turquoise, which is like doesn't get that dark.
Yeah. Okay. Well, you could. Okay. So then you can set it against a dark background because you have maybe control over the plot background.
Yeah.
But the other is maybe you can choose a muted color of that turquoise that the company will agree like reflects the family of
Or
that
maybe
color.
the answer is just like in your decision making, where you say, okay, you're going to make some decisions as you go through, and it's like, how much does the corporate color scheme really matter?
That's right.
In this plot?
That's right. And ultimately, like sometimes, okay, so there are times I think Morgan exactly right. Like we were trying to publish in a journal, and they were like, you need to make these axes black, and we're like, this is worse. But you know what? Like at the end of the day, the person paying you gets to make the final decision, even if they're bad decisions. Yeah. So, which they often are. That's fine though, right? That's just the way of the world. Yeah. So yeah.
Just trying to make it match the plot back or the slide.
But we could talk
background,
about it some if you want. Yeah. Yeah. Other questions? We have time. Yeah. So we have still 5 or 10 minutes so we can chat and then come back or yeah, unless there's more questions. Okay. So we'll come back in 5 or 10 minutes, I guess now. Yeah.
Yeah, so if you want to play with any of the tools we shared, we can like look over your shoulder. You can ask us questions, or if you have a visualization that you're wondering a little bit more about, we can try to give some pointers.
Or a color palette.
Color palettes, things like that.
Cool. All right, we'll be back in a bit. Okay, so I guess we'll be done almost. So I just want to like quickly summarize. I think the main points, other than always know what you're trying to say. But we talked a little bit about how you would pick qualitative or categorical things using these heuristics, and then some ideas of how you would quantitatively map color. I think those are the two broad things that we're trying to communicate. And then I just want to point out that people have done research on how different aspects of data are interpreted, like different ways of encoding data. And these are ordered left to right. And so this is sort of like that we spent a lot of time on color, but portion of the talk. So from left to right, these are the least effective to most effective ways of encoding data. So it turns out that if you take something and you change its position relative to a fixed scale, this is like the way people are best at extracting quantitative information, okay? Which is why we use axes on plots all the time. Things like length and angle are kind of okay. People get very confused about area and volume. But even past that, like if I were to ask you like how much bigger this is from that, most people would have a hard time accurately saying which one is like, is that double? Is that 1.5? That's a difficult thing for people to do. But color's like the worst channel, okay? So one thing I want to say, it doesn't mean color's useless. Just keep in mind that it's a weak way to give an indication of quantitative value. So you should still make good choices when you make color maps. Color maps are still quite useful. But what you're not giving somebody is like a really easy way to say like, oh, this is like twice as far away from that as that is from that. All right, you're giving people more generally just an impression of how does things vary over like space. Okay, and that can be very useful, but just it's really important to keep in mind that you're not encoding quantitative values in the same way that somebody's going to be able to unencode that. So keep that in mind. Okay, I guess if there's any last minute questions, there's another survey that I know there was one in the beginning. This is a closing one where we're trying to understand what people got out of this and what was useful.
Maybe the more important one, please.
You can have suggestions. You can be as brutally honest as you want. You will not hurt my feelings. I have a healthy ego, so you can be like, say whatever you want. What? And then the other thing I'll mention is, I think to start, it's the same survey link, so you can go to that slide. If you would like, and maybe this one works, I don't know. But as I said, the NSF is like paying us to try to like create resources and distribute them. So they will be on this website, which is like partially built at this point, but functional. So it has some information about color, but many, many other, it's like squarely focused on understanding graphic design and how it intersects with data visualization. Excuse me. You can
I can bring it up real quick. It's also very easy to find if you just Google data meets design. It'll look something like this. But like Dr. Lear said, there's a lot of general design things. So you can see color is in here. Since we just talked about it, I'll open it up. You'll see a lot of similar pictures and things that we just talked about, describing everything in a little bit more detail. But there's also all kinds of other things that you can look at in here if you're interested. So also let us know what you think about the resource. We're happy to add things as we go.
You don't have to be strangers. You can find our email address. It's pretty easy if you just Google our names at Penn State. So
yeah,
yeah, send us questions too. It's fine.
I can put our names back up on the screen as well. Are there any other final questions? We can also chat after if you don't want to ask now.
I'm just curious, have you done any legal consulting, for like exhibits and stuff, or?
No.
Okay.
The answer is, have I done any legal consulting? No.
Okay.
Yeah, I've never done any consulting that's not outside of the classroom. Yeah,
Okay.
yeah.
I was just telling him when you said don't necessarily ascribe bad things, or
Yeah.
intent, and sometimes there is,
Yeah, there often is. I just, I don't know. I try to be aware of when I actually know something, or versus when I'm telling myself a story that this must be malice.
Yeah.
Yeah.
It was kind of like what you said, the warm and cool colors, for the
Yeah.
litigant and the defendant.
Yeah. Oh, yeah, for sure. Yeah. I mean, this definitely happens, right? I also don't try to live in a world of like sunshine and butterflies. But at least from where I sit, there's a lot more ignorance than malice in the world. So yeah. Anyway, okay. I guess they're clapping.
Okay,
That
well,
we should
thank
be
you.
done. Okay.